Welcome to this presentation. Today we are going to discuss about link state routing. Link state routing has a different philosophy from that of the distance vector routing. In link state routing, if each node in the domain has the entire topology of the domain, that is the list of nodes and links, how they are connected, including the type, cost, and condition of the links, the node can use Dijkstra algorithm to build a routing table. And now we can see in the diagram. So the figure shows the simple domain with 7 nodes. Each node uses the same topology to create a routing table. But the routing table for each node is unique because the calculations are based on different interpretations of the topology. And this is analogous to a city map. While each person may have the same map, each needs to take a different route to reach her specific destination. The topology must be dynamic and representing the latest state of each node and each link also. And if there are changes in any point in the network, suppose for example a link is down, the topology must be updated for each node. How can a common topology be dynamic and stored in each node? Now, no node can know the topology at the beginning or after a change somewhere in the network. Link state routing is based on the assumption that although the global knowledge about the topology is not clear, each node has partial knowledge. That is, it knows the state, type, condition, and state of that link. In other words, you can say that the whole topology can be compiled from the partial knowledge of each node. Now, node A knows that it is connected to node B with matrix 5, to node C with metric 2, and to node D with metric 3. And node C knows that it is connected to node A with metric 2, and node B with metric 4, and to node E with metric 4. And node D knows that it is connected only to node A with metric 3 and so on. Although there is an overlap in the knowledge, the overlap guarantees the creation of common topology, a picture of whole domain for each node. In link state routing, 4 set of actions are required to ensure that each node has the routing table showing the least cost node to every other node. That is, creation of the states of the link by each node called the link state pocket, that is LSP. And dissemination of LSP to every other router called flooding and in an efficient and reliable way. And formation of shortest path tree for each node. Calculation of a routing table based on the shortest path tree. A link state pocket can carry a large amount of information. For the moment, however, we assume that it carries a minimum amount of data, that is the node identity, the list of links, and a sequence number and age. The first two, that is the node identity and the list of links, are needed to make the topology. And the third, sequence number, it facilitates the flooding and distinguishes new LSP from the old ones. And the fourth one, the age, prevents the old LSP from remaining in the domain for a long time. LSPs are generated on 2 occasions. One, when there is a change in the topology of the domain. Triggering of LSP dissemination is the main way of quickly informing any node in the domain to update its topology. And the second one is on a periodic basis. The period in this case is much longer compared to distance vector routing. As a matter of fact, there is no actual need for this type of LSP dissemination, and it is done to ensure that old information is removed from the domain. The timer set for periodic dissemination is normally in the range of 60 minutes or 2 hours based on the implementation. A longer period ensures that flooding doesn't create too much traffic on the network. After a node has prepared on LSP, it must be disseminated to all other nodes. That you can see in this diagram. Not only to its neighbors, and this process is called flooding and based on the following. First step is the creating node sends a copy of the LSP out of each interface. And second one is a node that receives an LSP compares it with the copy it may already have. If the newly arrived LSP is older than the one it has, it discards the LSP. If it is newer, then the node does the following. It discards the old LSP and keeps the new one. Then it sends a copy of it out of each interface except the one from which the packet has arrived. And this guarantees that flooding stops somewhere in the domain where a node has only one interface. Now let's see the formation of shortest path tree using Dijkstra algorithm. So after receiving all LSPs, each node will have a copy of whole topology. However, the topology is not sufficient to find the shortest path to every node. So a shortest path tree is needed. And a tree in the tree is a graph of nodes and links. So one node is called the root, and all other nodes can be reached from the root through only one single route. A shortest path tree is a tree in which the path between the root and every other node is the shortest. What we need for each node is a shortest path tree with that node as the root. The Dijkstra algorithm creates a shortest path tree from a graph. The algorithm divides the nodes into two sets, that is tentative and permanent. It finds the neighbors of the current node, makes them tentative, examines them, and if they pass the criteria, it makes them permanent. And we can informally define the algorithm by using some flowchart and let us apply the algorithm to node A, for example, graph to find the shortest path in each step. We need the cumulative cost from the root to each node, which is shown next to the node. So we have to follow the 3 steps. At the end of each step, we show the permanent or filled circles and tentative nodes and list with the cumulative cost. So we make first node A the root of the tree and move it to the tentative list. Our two lists are permanent list empty and tentative list is A of 0. Node A has the shortest cumulative cost from all nodes, that is in the tentative list. We move from A to the permanent list and add all neighbors of A to the tentative list. Now therefore our new list will be permanent list is A of 0 and the tentative list is B of 5, C of 2 and D of 3, right? And now node C has the shortest cumulative cost from all nodes in the tentative list. Therefore, we move C to the permanent list and node C has 3 neighbors. But node A is already processed, which makes the unprocessed neighbor just B and E. However, B is already in the tentative list with the cumulative cost of 5. Node A could also reach node B through C with a cumulative cost of 6. Since 5 is less than 6, so we keep node B with a cumulative cost of 5 in the tentative list and do not replace it. So therefore our new list will be permanent list is A of 0 and C of 2, tentative list is B of 5, D of 3 and E of 6. Now node D has the shortest cumulative cost of all the nodes in the tentative list. So now we move D to the permanent list and node D has no unprocessed neighbor to be added in the tentative list. Therefore our new list will be A of 0, C of 2, D of 3, B of E and E of 6. And node B has the cumulative cost of all nodes in the tentative list. Now we move node B to permanent list. So we now need to add all the unprocessed neighbors of B to the tentative list and this is just node E. However, E of 6 is already in the list with a smaller cumulative cost. The cumulative cost to node E as the neighbor of B is 8. So we keep node E of 6 in the tentative list. Therefore, our new list will be permanent list is A of 0, B of 5, C of 2 and D of 3 and tentative list is E of 6. And now your node E has the shortest cumulative cost from all nodes in the tentative list. So therefore, we move E to the permanent list and node E has no neighbor. Now the tentative list is empty and we stop here. And our shortest path tree is now ready. So the final list is permanent list is A of 0, B of 5, C of 2, D of 3 and E of 6 and tentative list is empty now. So each node uses the shortest path tree protocol to construct the routing table. The routing table shows the cost of each reaching each node from the route. So we can define the routing path now. And the open shortest path first protocol is intra-domain routing protocol based on link state routing. Its domain is also an autonomous system. To handle the routing efficiently and in timely manner, OSPF divides the autonomous system into areas. An area is a collection of networks, hosts and routers, all contained within the autonomous system. An autonomous system can be divided into many different areas, and all networks inside an area must be connected. Routers inside the area flood the area with the routing information. At the border of an area, special routers can be formed, and routers at the border of an area, special routers called area border routers summarize the information about the area and send it to other areas also. So among the areas inside the autonomous system is a special area called the backbone. So all the areas inside the autonomous system must be connected to the backbone. In other words, the backbone serves as a primary area and the other areas are secondary areas. This doesn't mean that the routers within the areas cannot be connected to each other. The routers inside the backbone are called backbone routers, and the backbone router can also be an area border router. If because of some problem the connectivity between a backbone and an area is broken, a virtual link between routers must be created by an administrator to allow continuity of the functions of the backbone as a primary area. So each area has an area identification, and this area identification of the backbone is 0 here. Then the Ospf protocol allows the administrator to assign a cost called the metric or to each route, and the metric can be based on types of service. As a matter of fact, the router can have multiple routing table, as you can see here, and which is based on different type of service. So in OSPF terminology, a connection is called a link, and there are 4 types of links that have been defined, that is point-to-point, transient, stub and virtual link. A point-to-point link is connects the routers without any other cost or router in between. And in other words, you can say the purpose of this link is just to connect the 2 routers only. And an example of this type of link is 2 routers connected by a telephone line or a T line. And there is no need to assign a network address to this type of link. And graphically, the routers are represented by the nodes and the link is represented by the bidirectional edge connecting the nodes. The metrics, which are usually the same, are shown with the 2 ends in one for each direction, and each router has only one neighbor at the other side of the link. A transient link is a network with several routers attached to it. The data can enter through any of the routers and leave through any router. All LANs and some WANs with 2 or more routers are of this type only. In this case, each router has many neighbors. For example, if you consider the Ethernet, router A has router B, C, D, E as neighbors, and router B has routers A, C, D, E as neighbors. And if we want to show the neighborhood relationship in the situations, we have to show using the graph method. So this is neither efficient nor realistic. It is not efficient because each router needs to advertise their neighborhood to 4 other routers for a total of 20 advertisements. So it is not realistic because there is no single network between each pair of routers. There is only one network that serves as a crossroad between all 5 routers. Thank you.